Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are at lecture 56 today. In the last lecture we discussed about a thin layer of adhesive with spatially varying modulus, and a flexible plate is lifted off this particular adhesive, and then what kind of torque that is required to propagate the crack at the interface. So, we derived those equations, and those equations were to be solved numerically, and we also presented some results. So, these results were there in my paper in this 54-55 over here. So, today I will like to discuss about two things. One is the adhesive layer with spatially varying thickness and modulus. So, in the last lecture we talked about adhesive layer which had a spatially varying modulus, but today I will like to include also thickness to it. And then after we finish that, we will like to talk about adhesion of viscoelastic spheres. So, viscoelasticity will be brought into our discussion. So, in a sense what we have here, then adhesive layer with its thickness varying by let us say sinusoidally and by according to this function, and then its modulus also varies according to this equation, and there are this kh and k mu, these are the wave numbers, and delta h, delta mu. So, these are the amplitude function or like that. And so, this variation in thickness and modulus, they can be in phase or can be slightly out of phase. There can be all kinds of possibilities that can be there, and now a flexible adherent plate is brought in contact with it, and initially there is a contact line that is formed because it is not in complete contact, but a spacer or a little load is applied, F that has been applied. So, this variation in modulus and the thickness, these variations are not that large, it is actually small, so that this contactor is flexible enough that it can remain in intimate contact with the surface of this particular adhesive having this spatially varying thickness. So, that is the thing. So, now we have to solve the elasticity equation that the way that we had done it previously, and which we have gone through several times. So, after we apply the lubrication approximation, and we can obtain these equations which we derived from this dimensional analysis and all that, and this is the incompressibility relation. So, these equations that we have derived earlier, in earlier we had mu is constant, but now it is not mu constant, mu is a function of x, and then these are the boundary conditions. So, boundary condition at z is equal to 0, this u is equal to w is equal to 0, and at z is equal to h, this u also is equal to 0. So, we will consider that no slip boundary condition, and like that, and then we also have w. So, w will be equal to some quantity zeta like this and and then the pressure, normal the continuity of normal stress at the interface of adhesive and the flexible adherent, that has to be considered. So, this is basically this quantity. So, one can integrate this equation and obtain this solution of for u and under these boundary conditions, and then one can use this incompressibility relation. These things we have done earlier, and we can get an expression for this z components of displacement, that is zeta x at a function of at h. So, one can get this expression. So, you will see that this equation looks basically somewhat different from what we have obtained earlier, and that is because of these functional forms that we have to consider now. And here we will also obtain, we will also substitute for P. So, the P is the pressure, and remember that the pressure has to be equal to the bending force that has been there because of the deformation of the film at the surface. So, the surface, this film undergoes deformation over and above its topography which is undulatory, and that deformation okay, the bending force because of that is actually this quantity, P is equal to d into d to the power 4 xi x by dx4 or zeta x by dx4. So, we will substitute this P is equal to this function into this equation, and finally, we have this sixth order equation. So, remember that this in this sixth order equation we have to solve this, and for that boundary conditions that we already we have described, similar to that we have to describe, we have to solve, and we have to keep in mind that as far as this plate is concerned, that the plate undergoes this deformation, but also this particular deformation, and that is because of the undulation of the surface. So, at 0 to x2a we have to use this equation or like that. So, that is those more details are there in this paper. So, I am not going through all the results, but if you are interested you can go through and we can learn more about it. So, that is all I wanted to talk about today on this elastic problem. So, now I will go to discuss about this adhesion of viscoelastic spheres. So, viscoelastic brings in different dimension to the problem, and it is about the time. So, the JKR theory we have derived earlier for contact between this elastic spheres, adhesive contact, and where we considered this JKR theory in the limit of this linearly elastic material. Okay. So, there was a definite relation between stress and strain, and we used that. That was this Hookean law, we use that. And also remember that this kind of material, elastomeric materials, they remain soft and elastomeric because their glass transition temperature is well below the ambient condition. So, for example, this PDMS or polydimethyl siloxane or silicone, whatever you call it, okay, has got a glass transition temperature of minus 115 to minus 120 degrees Celsius, and so at room temperature it remains soft and elastic. And for this elastic spheres, this is important. Contact radius depends upon instantaneous contact load and the work of adhesion between the adherent surfaces. So, there is a work of adhesion, that is because of the surface energy or surface chemistry of this material. So, that is thermodynamic quantity. But in addition to that, for an elastic material, whenever we bring these two spheres in contact, and let us say that we apply some load over here, okay, and then instantaneously some contact area is reached. So, it is not that the load has been applied some few minutes back and the contact area is still increasing, or no, it does not happen like that. That is for elastic materials. For a viscoelastic materials, this contact radius depends upon the loading history as well. So, that means like if I continue to increase the load P, then the contact area will increase, or let us say these are viscoelastic materials. So, they will relax with respect to time. So, what is meant by that is the elastic modulus will also change with respect to time. So, as a result the contact radius will change. So, this particular aspect that needs to be considered when we discuss about this viscoelastic material. Now, for a elastic material, elastic spheres, two spheres in contact, when we apply this load over here, so there is a finite contact area that is reached, that is A over here, and we say that the size of the contact zone. So, contact zone means that wherever this happens, there is influence is there of this adhesion forces, that is actually much small with respect to the radius, contact radius. So, in that limit there is basically a sharp crack that appears. So, what it means is that sharp crack means that the radius or curvature of the crack is basically 0, and so at that limit the fracture energy is given by this quantity. So, what it means is that whatever energy that has been spent in order to open this particular crack, let us say, okay, that amount of energy, elastic energy completely goes into this crack tip. So, as a result this G is given by this particular relation, where Ki, that is the stress intensity factor in the of the first kind, type 1 crack it is called, and so here this E star we know that is the effective instantaneous Young's modulus of the material, and so that is given as 1 minus sigma 1 square by E1 plus 1 minus sigma 2 square by E2. So, sigma 1 and sigma 2 are the Poisson ratio, E1 and E2 are Young's modulus, and 1 by R is equal to here 1 by R1 plus 1 by R2. And so, here for this kind of material the work of adhesion can be directly equated to the fracture energy, and that is called Ki square by 2 E star. In essence, there is no dissipation here. Whatever energy has been spent, that goes into creating the new surfaces, and so therefore this equation remains valid. So for a perfectly sharp crack tip, so we have just described. So now a fracture energy of a viscoelastic material also can be given as G is equal to Ki square by 2 E0 star, where E0 star is the effective Young's modulus, instantaneous Young's modulus of the material. So these two spheres in contact, so that 1 by R is equal to 1 by R1 plus R2. Now here we introduce these two terms, this particular term what is called the compliance. So 1 minus sigma 1 squared by E1. So this particular term is called the compliance. So C is equal to 1 minus sigma square by E. Okay. So this defines that how much compliant this material is to follow, let us say, a contactor. Okay. So that should go inverse of E, because lower the E, lower the Young's modulus, softer the material, more should be its compliance. It is from that idea. So here we have got an effective compliance, which is C, can be written as C1 plus C2. Now this is for, and let us say for an elastic material, but for viscoelastic material, okay, we need to define it slightly differently. So there, as I said, that the Young's modulus, that will vary because that relax. So as a result, this compliance, okay, now Ct is replaced by what is known as C1 of T and C2 of T. So this is called creep compliance, and the creep compliance becomes a function of time, and over here this C0 becomes the compliance that is instantaneous. So at this particular point time, at instantaneous compliance, so that will be given as 1 minus sigma 1 0 square by E1 0 star. Let me see if I am writing it correctly or not. Oh no, star, this is star, no, this is E0 plus this is 1 minus sigma 2 0 square by E2 0. So that is the at instantaneous. So E1 0 and E2 0, and here this sigma 1 0, sigma 2 0, these are the instantaneous values for these two materials, or this for these two spheres. Now compliance corresponding to long time elastic response, that is given as C infinity, and that will be given as 1 minus sigma 1 infinity square by E1 infinity plus 1 minus sigma 2 infinity square by E2 infinity. So what it means is that that this particular has relaxed for long enough, and after that whatever this modulus or Poisson ratio that has been attained, and based on that what is this compliance, so creep compliance. So that is this C infinity. So here as I wrote, so elastomers are nearly incompressible most of the cases, so we can actually simplify it. So we can write that sigma 1 is equal to sigma 2, and that is equal to 1 by 2, and so this 1 minus sigma 1 square, let us say it is 0 1, let me write it like that. So that will be equal to 3 by 4. So 1 minus sigma 2 0 square, that will be equal to 3 by 4. So we can actually write it like that, because mostly these elastomers are nearly incompressible material. Now for a point load on an elastic half space, the vertical deformation at its surface was deduced as V at z is equal to 0. So means, like, let us say that this is an elastic half space. So the top surface of the elastic half space, so what we have this particular plane, and let us say there is a point over here. At this point some load has been applied. So this point has got this coordinate, let us say x dash y x dash y dash, and at that point some load P has been applied. So basically some load P has been applied over here. So because of that, so this is less dash x dash y dash with respect to some coordinates, and let us say that we have got this particular point at which I want to find out the deformation, and so this is what it will look like. But the deformation over here, this V at z is equal to 0, that I want to find out, and that was deduced as P by pi rho E star. So this the distance between these two points, okay, so here it is of course x y, so this was rho, so here this point is x y, okay, and so here the vertical deformation V at z is equal to at the surface was given as P by pi rho E star, right. We had derived it earlier. Now, we will use this expression. So, in terms of compliance, it will be written as, let us say, P by pi and rho and C, okay. So, or let us say C into P like this. So, now if it is instantaneous, so we will write it as C, and let us say we are talking about body 1. So, therefore, we will write it as P C10 by pi rho, P C10 by pi rho. Now, let us see that this P dA. Now, let us say that we want to find out that the load has been applied not to a particular point, but through at an area. So, remember that we had discussed this kind of problems earlier. So, let us say this is the circular area through which the loads have been applied. So, this is the center over here, and remember that we had discussed this earlier, that we have this particular point, this is the center, let us say O here, and this particular point, that was B. So, the distance from center to this B is R, and then there is a point over here. Let us say this point is at a distance L from here, right, and we had discussed these points earlier. And so, here let us say that this distance is rho from here, and this angle is phi over here. So, here there is a small area. So, this area will be given as rho into d phi into d rho, like that. So, we will come to that in a minute. So, this area is dA over here. So, because of the load at this point, at this point means at this point, let us say C, what is the deformation at B? That is what we want to find out. So, the infinitesimal area, this is dA, and so therefore, we will have, let us say, the infinitesimal deformation dV at z is equal to 0. So, that will be given as, let us say it is P and then C1, and let us say it is rho into pi into d of A, right, like that. Now, so now what happens is that there has to be a temporal effect that needs to be considered, because some point of time, let us say time t is equal to 0 over here, and we are this is time t is equal to 0, let us say, and this is time, let us say t, right. And now the load that has been applied, that the load is varying, or the compliance of this material, okay, creep compliance, that also varies. So, we need to consider that the effect, okay, with respect to time. So, temporal effect needs to be considered, okay, because this quantity, as I said, PC1, that changes over time, because pressure can also change over time, and C1, that is the compliance, that also changes. So, therefore, the contribution to V at z is equal to 0, that also changes over time. So, now how can you do that? Now, we will consider that, let us say there is a time over here, that is tau, and there is another time over here, that is tau plus d tau. So, within this time, the pressure varies from P plus dP over here. So, let us say here the pressure within this time, that needs to be pressure has varied. So, pressure varies from, let us say, P to P plus dP. So, the pressure that works on this time is actually dP, and so over here the compliance, okay, so that has the time effect of compliance, that will be there, okay, that has to be considered. So, that will be actually equal to C of t minus tau, okay, because this is C time t here, and the compliance that has been there at that particular point of time was for this particular time span, that needs to be considered, and so that span, because of that, the compliance part aspect that will be there is t as a function of t minus tau, okay, that time needs to be considered. So, and then we consider between this all these small time spans, okay, of dt, and integrate over time from 0 to t, that is all needs to be told. So, the time between t tau and tau plus d tau, let us say, and so as I said that for this is for body 1 SPR1, so it is 1 over here. So, during this time period of contribution of dP, okay, so that will be given as dV z is equal to 0, and that is equal to, this is equal to C1, and this is t minus tau, and into dP pi and rho and d of. So, here we can further write this p actually varies with respect to r and also time. So, we write it over here like this, this is C1 t t minus tau, and this is pi, this is rho here, and dp by d tau here, and d tau, and we need to integrate it with respect to time because the load has been started to be applied at time t is equal to 0, let us say. So, therefore, we need to integrate it. So, this quantity, okay, this effect we will integrate. So, this effect we integrate. So, this will look like this is pi and rho, and this is C1 t minus tau, and this is dp by d tau, and this is d tau, and this is 0 to time t. So, this integration is to be done. So, once this is done, so that is actually this effect, this integrand, okay, integration whatever we get. So, that is actually for this particular point, this particular point that I drew earlier. So, here see for this particular point, okay, for this area element around this particular point, because of which whatever is the effect over here with respect to time, that is considered, okay, with respect to the time 0, that particular is taken care of once we do this integration. So, this particular quantity is called C. So, this particular quantity which is actually 0 to t, and this is C1 into t minus d tau, and dp by d tau and d tau, and here actually we put a minus sign, that means at time t is equal to 0 this load has been started being applied, and so this particular quantity, this is called convolution. This is called convolution, and it is represented by C1, okay, over here star p, okay, by this expression. So, this is called convolution, and that takes into account the time variation, okay, of this particular parameter because of its viscoelastic effect. So, yeah, and so therefore, this integration part, that is given by this convolution C1 star into p, and pi rho is in the denominator. So, that is already there, and the convolution has this particular property that C into a star p, if this is equal to psi, then p will be equal to C inverse, okay, into star psi. So, this kind of like inverse can also be found out of this from this convolution theory, from the convolutions, it is called inverse convolution, and this can be, for this one actually uses what is known as Laplace transforms and all that. So, one can actually use that and find out this inverse convolutions. So, this what I am going to do it here is a very simplistic way, but then these things are can be found out or can be done. And I also wanted to point out that whatever I am going to say for this particular topic is actually available in this particular paper. So, you can compensate supplement to whatever I am saying by reading that particular paper by Professor Herbert Hoy at Cornell. So, here we are. So, we have obtained this convolutions. Now, we have to integrate it over this area, and for that let us say that this is this function, this is this area through which the load is being applied, and so here this is the point, this is B, and this has got a r, r is the distance of this particular point from the center. I have got this particular area over here, this distance is L over here, this distance is rho over here. So, the area is rho d phi, this angle is phi over here, okay, rho d phi into d of rho, right. So, this is the area of this portion. So, if I have to integrate it, then it will be V1 and R, V1 at z is equal to 0, and V will be a function of R and T, remember that, and so that will be equal to, let us say that over here. So, it will be C1 into C1 star, this is P and this pi rho, and here you have to integrate with respect to rho d phi into d rho, like that, and you have to integrate it over the area. So, that will be with respect to from area. So, area will vary from, let us say 0 to this is rho 1 here, and then over here it will be from 0 to 2 pi. So, rho will vary from 0 to rho 1 and phi will vary from 0 to 2 pi, like that. Now, here there is one idea, that is the maximum area of contact that has been attained, means that when this experiment is being done or these two spheres are being brought in contact. So, this contact radius is continuously increasing, okay. This is non-decreasing contact, that is what it means. So, therefore, that at any time t, whatever is the contact area that is attained, that basically is the maximum, okay. So, that is the one that is to be considered. So, if this is not the case, if it is not monotonically non-decreasing, okay, then there will be further complications in the analysis, okay, in terms of the math basically, but not conceptually much, but in terms of math. But then let us, to keep things simple, we will consider this, that the monotonically non-decreasing contact, what it means is the load is being applied, and because of that this area of contact that's actually is increasing, okay, that's what it means. So, here as I said, for this V2, that means the second sphere also we can write it like that, and so therefore we can add this both this C1 and C2, and so that will become is equal to C here, and so like that. Now what is the condition that these two spheres will remain in contact at any given r? So, that will be equal to delta, means the amount of distance by which these two spheres have been brought towards each other, minus r square by 2. So, delta will also be a function of time here, minus r square by 2r. So, that is the way it will be. So, delta minus r square by 2r, and so here we have already obtained this expression for this is equal to let us say the total A at time t, and this is C star P, and this is pi into rho. So, I have obtained here pi into rho into d of A, and so that will be equal to here delta of t minus r square by 2r. So, this solution, okay, of this equation has been obtained, okay, of the form that is obtained from the lecture 22-15 slide 15. So, we have obtained that, and this solution, okay, for the sake of for this adhesion condition, that can be actually written as something like this. So, so it will be C star, okay, P that should follow the similar form, this particular form, B0 into T into this is A square A of T square minus R square, and this is square root plus let us minus, let us say minus B1 of T, and this is square root of A square as a function of T, of course, minus R square, right. And this is everything is happening after time t is equal to 0. So, we use something called Heaviside within this area, within the area of contact only. So, let us say that this is actually given as A of T minus R, in the sense that this is applicable. So, this is Heaviside function. So, Heaviside function is A of T. So, as long as this quantity, okay, it is greater than 0, this is equal to 1, otherwise it is 0. So, here it is. So, this is less than 0. So, if this is negative, this is 0, if it is positive, then it is equal to 1. So, the expression, the solution of this C star P RT, so that is the convolution, okay, that solution has to be of this, it can be of this particular form. So, this we had obtained in the lecture long quite some time back, that is lecture 22. Now, what we need to do is to obtain some expression of this delta t, okay, and relate it to B0 and B1 by how? By substituting this expression, okay, into this, and then we will do this integration. So, I will take up this particular aspect in the next lecture. Thank you.